Hi everyone, so this is chapter 3, time varying field. Okay, so you can look at your own slide. So in the first chapter, you have learned about the electrostatic field, which that field is generated when there are stationary charges. And in the second chapter, you learn about the magnetostatic field, which is due to the steady currents. So for these two chapters, you are dealing with something that is static, not changes throughout the time. So in this chapter, we are going to deal with the time varying field, and these time varying field are usually due to accelerated charges or time varying current. So you are going to see how the electric field can be produced by a changing magnetic field through an experiment which is conducted by Michael Faraday. Okay, this is actually a video from YouTube, and I want you to look at it.
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right, and as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. And if I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also. We saw that as the number of turns in the coil increased, the current increased. So the current is proportional to the...
Okay. So what is your observation? Okay. What is your observation from this video? What happened in this video? So this person, okay, he prepared 3 types of coil. Okay, each of the coil they have different turns. Okay, some only 1 loop, okay, medium loop and a lot of loop. Okay, what happened is he hold a magnet bar, and then he insert the magnet bar into the loop. Okay, you can see the deflection, okay, appears on the amperes meter. Am I right? So what does it mean when there is a deflection? Current flow. Current flow inside the loop. Okay? So you can find that when the turn of the loop increase, okay, when you have many loops, okay, it increases the deflection. More current is generated. Okay? And when the speed of the magnet increase, okay, when you slowly put in the magnet and when you put in the magnet very quickly, what's the difference? Okay, it increases the deflection. Am I right? Okay, and when the magnet moves in different directions, the deflection will be in different direction. What does it mean when the deflection is in different direction? Current flow in the other direction. Okay, Okay, current flow in the other direction. And by moving the magnet bar in or out the loop, okay, it creates deflection in the ampere meter and shows that there is a current flowing in the loop. And if you found that if you maintain the position of the magnet inside the loop, there will be no current flowing. Okay, so in other words, it means that if you want the current to exist in the loop, there must be something moving and there must be something changing. If no changes, everything maintains static, then it won't have any current. So this is the principle of Faraday's law and how it is used to generate electricity. Okay, but this one is a simple concept. Huh? Okay, so the Michael Faraday, okay, and Joseph Henry, okay, according to their research and work, okay, a static magnetic field does not produce current, okay, like what I explained just now. But a time varying field produces an induced voltage called electromotive force or simply EMF in a closed circuit, which causes a flow of the current. So when there is a change of the magnetic field, time varying field, when you move the magnet bar, okay, in and out from the loop, you are actually changing, okay, the magnetic field. So the magnetic field is time varying parameter. It is not constant because you move. Okay, so in this chapter you are going to see, okay, you are going to learn how to calculate the induced voltage, okay, the induced VMF, okay, at different conditions. Okay, we can have different conditions. So an EMF, okay, can be generated in a closed conducting loop under three conditions. Okay, you can generate electricity. Okay, there are three conditions. First one, a static loop in a time varying magnetic field. This is something that you saw from the video just now, right? Okay, when you remain the position of the loop and you insert and take out the magnetic bar. Okay, when the current is generated in this way, we call the generated EMF as transformer EMF. They got their name. You have to remember their name because different types of EMF, they have to use different formula. I cannot mix both of them together. And for the second case is a moving loop or conductor in a static magnetic field. Okay, later we will look at this one. Okay, how this thing happen. This thing is actually you maintain, okay, the position of the magnet or the intensity of the magnetic field. You didn't change it. It is always constant. But you move your conductor. Okay? So that when you move your conductor, okay, your conductor tends to cut. Okay? Tends to cut the magnetic field. Okay, for example, magnetic field is pointing upward. Okay? Pointing upward, you just imagine. And if you move your conductor here and there, you are actually cutting the magnetic field, cutting the flux. Okay, for this one, when there's something moving, the conductor is moving, very easy. It is called motion EMF. When there is something moving, motion. When there is nothing moving, then it is transformer EMF. You must be able to differentiate both of them, okay? And the last one, a moving loop in a time-varying magnetic field. And this one is actually the combination of these two. And when the loop is moving, and the magnetic field is changing with respect to time. Okay? Any questions about the definition of this EMF? You understand, eh? So let's look at the condition. The condition and what happened. So now imagine you have a loop. Okay, this one is your loop. Okay, a conductor, and this conductor you connect it to a resistor. Okay, and this conductor now you putting it in a static position and static condition. Okay, you didn't move it, just put it there. Now you introduce a magnetic flux density, or you introduce magnetic field. Okay, you put in this loop in an environment that has magnetic field. And if you look at this one, this is B bracket T. Am I right? What does this mean? This means that this B will change its value at different time. So it is a time varying magnetic field. Okay? Time varying magnetic field. So to calculate the voltage EMF, the transformer EMF, Look at this one, TF, transformer EMF. This condition is a transformer EMF because the loop is not moving, right? And only this B is changing with respect to time. Okay, the transformer EMF will be equivalent to this equation. So this will be the equation that you have to remember. After in the exam, after you have identified what types of EMF that appear across these two lines, okay, you have to recall back what is the equation that you have to use. So for the V transformer EMF, this will be the equation that you have to use. Okay, what is the meaning of the parameters here? N is the number of turns. How many turns you have? If it is 1, then it will be like this. 1 only, 1 turn. Okay, what happens if you have more turns? This one will increase, right? You have more turns, more N, this one will increase. So this is what you observe from the video. Okay, when you have more loop, the diffraction will be bigger because the generated transformer EMF will be larger. Okay, next one, you have to integrate. Integrate what? Integrate the partial differentiation of this B. Okay, when given this B, you have to differentiate it first with respect to time because this B is an equation, right? And this equation depends on the value of t. So you have to perform partial differentiation. Do you still remember partial differentiation that you learned in Max 3?
No.
Then, do you want to retake Max 3? No. Okay, try to recall back how to perform partial differentiation. And you have to dot product the surface. What is the surface here? Surface is the surface of the loop. Okay, the loop. So if you look at this one, this is a circular surface, right? So this ds will be r, dr, d theta. Depend on the shape of your surface. Okay, the surface can be rectangular, right? Can be circular. So depends on the shape of your surface, then you define your ds. Okay, so after you get your v, sometimes question will ask you to find what is the current because you have calculated the voltage. Can you calculate the current as well that is flowing inside this loop? Then what you should do? Okay, so the formula to calculate the current is very easy. V equals to IR. Very easy. But here look at this one. Okay, it actually includes the internal resistance. Internal resistance of this cable, of this wire. Okay, if the question said that this thing is very small that you can neglect, you just assume it to be 0 and consider this R in order to calculate your I. Okay, just now from the video you see, right, when you enter the magnet bar, okay, the needle will deflect at one side. When you pull it out, it will deflect the other side. And I explained that is because the changing of the current directions. So, how to determine the current directions? Okay, the current direction is actually determined or governed by Lenz's law. Okay, you have to identify the direction of the current. Then how? Using the Lenz's law. So this Lenz's law it says that the current in the loop is always in such direction as to oppose the change of magnetic flux that produces it. Do you understand what does it mean?
No.
Okay, look at this figure. Can you see the green arrow?
Yes.
So this is the direction of the magnetic field, right?
Yes.
So now that current must produce another magnetic field which opposes the direction of this green arrow. Means now the green arrow is pointing out. Okay, the current must produce another magnetic field that is pointing downward. Okay, can you see this one, this circle? Okay, this circle shows that this B induced must oppose the direction of the original magnetic flux. If this one is going up, use your hand, you have a loop, right? The generated magnetic field must be going down. Can you imagine? If you have a loop, right? Your loop, magnetic field is going up, right? So you must have a current that is able to produce a magnetic field that is going down. So you use your finger. This is the direction of the magnetic field, right?
Yeah.
Going down. If it is like this, going up, right? Wrong direction. So it must be like this. Then only oppose the original direction of the magnetic field. So when your magnetic field, when your forefinger is pointing down, so this one will be the direction of your current flowing. Can you see? Okay. So your current, look at this figure. Your current will flow in this direction. Okay? When your current flow in this direction until here, this will be the positive, right? And this will be the negative. And continue to flow. So this point is a positive. Okay? And complete one loop. What happened? This is, for example, if this condition is the condition when you insert the magnet bar, what happened when you take out the magnet bar? This one will downward, am I right? You assume, just assume, This one will be downward. So the current produced must be upward. Okay? This is the case when you take out the magnet bar. So now the current produced must produce the magnetic field that has upward direction. So now your current will flow in the other direction. That's why you see different deflection in your ammeter. Okay? Can you understand the concept? Yes, So this is the Lenz's law. Lenz's law that said that the current must exist by using this concept. You have to remember, because in the exam you have to predict the direction of the current based on this concept. Okay, there is no calculation. The calculation can only give you the value, but they cannot give you the direction. You must use the Lenz's law to identify the direction of your current. Are you clear? Yes, Very good. Okay. So this one is actually a process to rewrite, this formula. This formula. Okay, so I think you see this formula before, right? I think you had this equation. Okay, this equation is previously we used it to calculate the voltage, at one position. Okay, this is actually the transformer EMF is actually a voltage. So if you put these two things together, when the N is equals to 1, what happened? I apply the Stokes theorem. Stokes theorem is to transform the line integral, line integral to surface integral. And I compare again these two things, and I can say that, the curl of electric field will be equivalent to the negative of partial differentiation of magnetic flux density. This one is actually just rewrite it because we are going in time varying field. Your Maxwell equation, previously is this one, right? For static condition will be replaced by this one. Do you remember this four-set equation that I show you at the end of almost the end of the chapter 2? Do you remember? The one is only applies for static condition. The charge is not moving, the current is DC. But if your charge is moving and it is a AC current, so this one we're going to replace this thing. Okay, you got some idea? Okay, this one later on. I want you to understand the concept first. Can you try this exercise? Can you? Now you have an inductor. It's formed by winding ends of thin conducting wire into a circular loop of radius A. You have wire and then you loop it. End turn. And the radius of the loop is A. Radius. So this inductor loop is in the XY plane. XY plane. Do you know what is XY plane? Yes, no problem. XY plane. With its center at the origin. It is connected to a R, and in the presence of a magnetic field given by this one. So find the magnetic flux linking a single turn of the inductor. Okay, first of all, when you have this condition, you know that there is a flux, okay, cutting the loop. First of all, you need to know whether it is transformer EMF or motional EMF. Is it something moving? Is the conductor moving? Is the velocity given? No. No, eh? So it is a transformer EMF. Some more, when you look at your B, right? Can you see the T? This means that this T will, when this T change, the value of the B will change. Okay? For this Y and Z, they are just direction. They are just direction, nothing to do with the variable. Okay? So when the T change, B will change. So this one is a time varying magnetic field. The first one, the magnetic flux linking a single turn of the inductance. What is magnetic flux? What is magnetic flux? Okay, this one I redraw the circuit. Okay, so this is the parameter given by the questions, right? Okay, first one they are asking you to find the magnetic flux, right? Magnetic flux, okay, linking a single turn of the conductor. So what is the symbol of the magnetic flux? Do you remember? Oh no, we are not using this we are not using this symbol, sorry. We are using this symbol. Do you remember this symbol? This is a symbol for the magnetic flux, and it is equivalent to you integrate the B dot ds. In case you don't remember, you learn this thing here, right? Where is the, yeah, can you see this one? The magnetic flux through a surface, okay? So if you want to know the magnetic flux, you integrate the B dot dx, okay? B dot dx, eh? So we come back here. So what is your B? Is this one, am I right? Given by the question, eh? So B naught 2y plus 3z and then sine omega t, right? There is a dot here. Okay, what is ds? ds is the surface of your loop. Your loop is in circular surface, am I right?
Yeah.
So what kind of coordinate system that you have to use? Yes, cylindrical. Okay, so look at the ds for cylindrical. So this one is the ds for cylindrical, right? So which one you want to use? Okay, which one you want to use? This is your surface, eh? You just imagine this is a circular surface. It is located at plane xy, right? So the surface is normal to direction z. Am I right?
Yes.
So your ds, you have to pick the third one. Okay, you have to pick the third one, which is this one, eh? Surface is this one. Okay, so here we come back here. So here it will be r dr d theta, and this surface is a bowl surface, right? So you have to insert the direction, which is z direction, eh? Sorry. Okay, z direction, eh? Okay? Can you follow? Okay, so here you have dr d theta, right? So here you must have two symbols of integration because this is ds. Okay? Boleh? So next. Okay, you have to define the interval, right, of your loop. It is a circular loop. And what is the radius? Okay, so for the radius, it will be from 0 up to and the angle will be from 0 up to 2 pi. Okay, it is a complete circle. So can you perform the integration? Can you perform the integration? Please try it. Oh, no. Before we perform the integration, we need to settle down the dot product between the direction. Am I right?
Yes.
Okay. So we settle this one first, huh? Okay, we take the variable, we take the constant out. Okay, so this one will be B naught sine omega t, and you have a R, right? Here is 2y plus 3z, and then you have to dot product with R is here already, so you have dr, d theta, and z. Okay, now one by one, I just rewrite it. Okay, one by one. Okay, this one dot product with the z, what you will get? This is dot product, not cross product, So what will happen? If you forget, look at this one. What will happen if you dot product something that has different direction here? 0, right? Okay? 0. And only when you dot product the vector with same direction, you will get 1. So whatever, when they are in different direction, 90 degrees difference is direction, it will be 0. So you left this one. So 2 pi A, and then this one will be 3, okay, B naught, okay, R sine omega t, because this one 0 already, right? This one, when you dot product with the z, you will get 1. That's why this one remain, this one becomes 0. So you will have dr d theta. Then only you can start solving your integration, your double integration. Can you solve it first without looking at my solution? Okay. I missed the B, right?
Yes.
Okay. So this one will be your magnetic flux, right? Okay, this one will be your magnetic flux. check. Okay, the unit is Weber. Okay. Okay, this one is a unit. Okay, so this one is the solution for question A. Who cannot get it? Okay, right? Okay, let's look at B, what they want. Okay, B, the transformer EMF when the N is equals to this one, the B0 is given this one, the A is 10 centimeter, and the omega is 10. Okay, they give you all the values of the parameter. Okay, transformer EMF. So what is the formula for the transformer EMF? Okay. Okay, B, you have to calculate the transformer EMF. Okay, there is one equation that you have to remember, right? Negative, and after that, integrate B. Okay, and then okay. So what is the things that you should find first? This one, right? Okay. This one actually you have to do it, right? If I split it, am I right? Can you see this thing? So this one, have you calculated it? Have you calculated it? Yes, right. So this one is the magnetic flux that you have calculated in question A. So what you will do is, you just replace it here. Okay? This one, right? Is it right? Okay, so can you perform the partial differentiation with respect to T for this magnetic flux? So just now we have 3 pi A square and then B naught and then sine omega T. Is it? Okay. Okay? Am I right? Now, you have to differentiate with respect to T. So what will happen? Constant, they are all remain. And this thing, when you differentiate, it become, and then yes, don't forget the omega. You have to multiply the omega, right? Okay. Now put in the value that you get from the question. Question say what? N equals to, this one just cancel it, 10, okay? 10, and then your A equals to 10 centimeter, okay? And your B naught equals to 0.2, right? And what else? Omega equals to 10 power 2, right? 10 power 3, okay, 10 power 3. So can you get the transformer EMF? I want you to calculate yourself. So for the A, you have to include the CM together. Omega T. And you still have one here, omega, Okay, so this 60 pi is equals to 188.5. Okay, they are the same, eh? Same as the answer in the slide, eh? This one. Same, eh? Okay, I proceed to question C, okay? C, what is C? Look at C. The polarity of this one at t equals to 0. So it means that they want you to calculate what is the value of this transformer EMF when the time equals to 0. So it's very easy, right? You just take this equation and then you replace the t to be 0. Okay? This is transformer. Okay. So when this is 0, it will become cos 0, which is 1. So you will get this one, right? Okay. So this one will be your voltage when the t equals to 0. Okay. Very direct questions. No problem on this one?
No.
Okay, we go to the D. What is D? The induced current in the circuit, okay, when the R equals to 1 kilo ohm. Okay, so they want you to find the I. I, eh? So what is I?
V equals to IR, so I equals to V over.
V over R, right? The general one. So you have this EMF.
So
Yes.
the formula is even the VEMF over the I. The
Yes,
R,
yes, yes.
both
Ri plus the R, right? So actually this R represent the R that is directly connected to the loop. And this Ri is the internal resistance of the wire. So if the question didn't say anything about the internal resistance, just assume it to be 0. Okay, everyone likes 0, right?
No, I don't like.
Okay,
I
so
want to try.
okay, this one EMF So you take this negative
Negative
6.
0.19.
Okay, divide 1K. Okay, so
Negative 3 over
Oh.
55.
they don't want you to use this one because they didn't specify about the time, eh? So they want you to take the whole equations. Okay, so 60.
Negative 3 over 55.
Okay, pi. Okay, so 60
Negative 3 over
pi 1000, eh? So it will be 5. Sorry, it will be 3 pi.
over 50.
Yes, over 50. Okay.
Cos.
Okay, this is together, eh? Okay, so this one will be your I. What else? Is it okay, this one? Everyone, you can follow? Yes, huh? Huh? Yes, thank you, Ampere. Okay? Now, let's move on to the last one. E, eh? What is E? Look at. What is the transformer EMF if now I change the B to this one? Okay, initially you have your B, this one, am I right? Now I want to change your B to this one. Okay, only Y direction, no more Z direction. Okay, what will happen?
The plus equals to 0.
Huh? What will happen?
The plus equals to 0.
Okay. Is everyone know the answer? Do you know why?
Yes, that's why. Sine omega t. Y.
What is the direction, eh? Now I want to change the B to this one. What will happen? Then the question asks you to explain. Okay? Good, do you know why? Yes. Yes, huh? The others, how about you? Do you know why?
Because of different direction.
Yes. Okay? Do you remember what happened here? Okay, for the Y. At the beginning, when we calculate this one, do you remember what happened to the Y? Zero, right? If there is only Y, this thing doesn't exist, the whole thing will become?
Zero.
Okay? So you just explain. So everyone said zero, so what you should explain here?
Zero.
Just write zero here?
Because of different direction.
So you have to explain, You have to explain. Explain something that I understand. Not just zero, I don't understand. Okay? So you have to explain why, So type something here, write something here. When the B is in Y direction, okay? The cross product between the B and dx will cross product. Yes, you are right. Dot product, okay, between the B and S will be
Zero.
zero. Okay, if you're afraid, still don't understand, you can write it out. Okay. Dot ds, right? So you just don't need to insert the whole equation. It's also alright. You just say that this one is y. Okay.
Yes, the product.
Okay. Yes. The r d theta is the z. Okay.
Zero.
So this one will become 0. Okay? So this one will be your explanation for the E. Okay. Oh, very easy. What will be the direction of the current? What will be the direction of the current? Huh? What will be the direction of the current? It is actually pointing up, right? Or even though it is not straight up. It is because it is a combination. The B is a combination of Y direction and Z direction. Okay, Y and Z. That's why you see this thing. Okay, it is not straight up or straight down. Okay, it is something like this. So it means that you have to produce something down. So what happens when your Z is what will be the direction of your current if I want the magnetic flux to be down? Down, right? I mean, this one is okay. This one is not straight. Okay, it's not down, but sengit, right? Okay. But if you look at this one, it is positive, right? Positive. So we can consider it as something going up. So you must have something here, right? Going down. Sengit down. Yes. Very good. Sengit down. Okay. Mama, okay. So when it is down, okay, this one will be your direction. Okay, the current will flow in this direction. Okay, in this direction, and positive, negative. See this current? And here will be positive and negative. Okay, you get some idea?
Yes.
Okay. Okay, let's look at. So this is all about the transformer EMF that involve the loop with, yes? Oh, they consider all. Okay? Okay, you are talking about the current, right? Okay, imagine the current flow like this, right? We enter the loop, it will turn until at the end it come out again. So for all the loops, okay, same current. Okay, same current, So let's go back to the Second EMF? Okay. Second EMF, are you ready?
Yes.
Okay. So I want to continue the next EMF. The next EMF, you have learned the transformer EMF and its equations. Now we'll proceed to the motional EMF. Okay? How does the motional EMF happen? Okay? All these, they are derivation, and this one actually related to the force that you previously calculated. Okay? The force on a charge when it is moving with certain velocity and in the environment that has magnetic field. You learned this in chapter 2. Okay? By taking this equation and relate it with the motional electric field and replace it here. Okay, and replace it here. Finally, the motional EMF. Can you see the M? M stands for the motional EMF. So the motional EMF will be equivalent. So you integrate the U, how fast your current or your loop is moving, cross product with the magnetic field, the constant magnetic field, and the L is here. Okay? This is about the motional EMF. And look at how this thing actually happened. Okay, look at this figure. So you have magnetic field, okay, which is in what directions? So they didn't specify. In the Z directions, I assume it is in the Z direction. This is your magnetic field. And now you moving this sliding bar. This sliding bar is touching two rails here. Yeah, two rails. You just move it. So when you move it, okay, you change the area. Am I right? Okay, you some sort like you move or you cut the magnetic field, okay, by using your conductor. Okay, so this is where you apply this formula, motional EMF. Okay, so you move this sliding bar in this direction or that direction. Okay, we look at one example. This one. Then you will be clear how to use it. Okay, so can you prepare for these questions? Do you understand the formula just now?
I have to see one example.
Yeah, this is the formula that you will use. This one. Motional EMF, integrate this one. Okay? U cross B dot dl. Later we will use this one to solve for the motional EMF.
What is the last one?
This one is for a moving rod between a pair of rails. They already straight away taking into consideration the length, the speed. Okay, and this one they consider the, what is this? This is F, the force. Force for a moving rod between a pair of, okay. Okay, this one is F integrate I dl cross B. Do you remember the force that you learned in chapter 2? This equation is from here. This one. Okay, when you integrate, you get, I is a representation for current, right? L will be the length.
So that one is already integrated?
Yes, it's already integrated and the B. Okay, it's taken from here. Okay, so I want you to refer this question. Okay, refer this question, okay? Are you ready for this exercise too? Yes. So you have a rectangular loop. Can you see the loop? This one is your loop. Okay, rectangular loop. Okay, and it has a constant width L. So L, look at the labeling. The L will be the length from this point to this point. Okay, L. Okay, the length increase, okay, with time. This is your x0. Can you see x0? So it means that this thing you will move, okay, from time 0, okay, from when the time is equal to 0, it will at this position. When you increase the time, then it will be at different position. So note that the B increase linearly with the x. So this one is your B. So when your x increase, your B will increase as well. Okay. So the bar starts from 0 at t equals to 0. So first one, investigate the motional EMF across the rectangular loop. Have you found that actually I make this wording to be in red color? So these are the normal wording that you might find in your test or final. Okay, so they're actually just a wording. So as a conclusion, they want you to find. That's the things. Okay, so don't be scared by all these wording. Analyze. I never analyzed before in class. No, don't worry. You just need to find only. Okay, illustrate. Okay, illustrate. Illustrate means you have to draw, right? Things like that only. Okay, so normally in the exercise during lecture section, we will use easier word: find, determine, calculate. Okay, all this wording can be replaced by this wording also. So don't be scared that okay, after you see this wording, you cannot do anymore. Okay, like a psychological issue. But this shouldn't be something that actually stop you or disturb you when you want to answer question in the final test. Okay, so first one, investigate the motional EMF. Okay, this sliding bar is moving, so the magnetic field, the magnetic flux is not changed versus the time, so it will be a motional EMF. Okay, motional EMF. So okay, so this one will be my drawing. So for motional EMF, you have to use this equation. Okay, totally different equation compared to previous one. So the first thing when you're dealing with the question related to Faradays law, you must identify motional EMF or transformer EMF, because both of them they use different formula. Okay, so let's look at the U. Do you know the U? Okay, you know the U is the speed, right? Okay, you don't know its value. Okay, you represent it with a variable U. And do you know its directions? When you are dealing with this kind of question, it will always together, the question will always give you this, okay, this diagram together, to show you, okay, when it is moving in this direction, it is X direction. If moving in this direction, will be Y direction. And your B will be Z direction, Z direction. If your B is negative, if this symbol is crossed, your B will be in the negative Z direction. You have to look at this one as your reference. So your U will be in the am I using the wrong Z? Okay, sorry, this one I'm wrong. So this one is X and Z. Okay. So the motional EMF. How about the B? B is this one, right? So what is the DL? DL is the length of this sliding bar. Okay, something that can move. So this DL, the length is depend on the value of Y. So here it will be dy. Okay, U dot X. What is the cross product in between X and Z? Negative Y. Okay, you have dy here. Okay, what should be the interval? What should be the interval? Okay, do you know the length? The length is L, right? Okay, so the answer will be U B naught X and L. U V naught X and L. Volt. Is it correct? E L T O K. The answer is this one, right? B naught U square L T. B naught U square U square LT. Where the T from? And why the U become square? Why the X disappear? Any idea? Any idea why? It's related to the velocity is equals to the distance divide time. Can you relate with this one? So x will be the distance here. Okay, from here up to any point, the distance. And this distance is depend on the speed, right? Okay, so you can replace it with u v naught. Okay, velocity u multiply with the t. Okay, will be the distance. Okay, u equals to x over t. So what is x? X is the distance. Okay, 0, 1, 2, 3, 4 until here. Okay, x. So when you divide the distance with the t, you will get the speed, the velocity u. So here will be L. Okay, so when you put them together, you will get the same answer as the answer in the PowerPoint slide. U square, B naught, T and L. Okay, so this one will be your motional EMF. Anyone still don't know how this X is converted to this UT? Do you know? No idea. Okay, imagine here you have a sliding bar, right? At t equals to 0, where is the location of this sliding bar? It's here, am I right? So it will move slowly in the positive x direction. Okay? At the end, okay, it will reach a distance x. Okay? I don't know what is the value of the x. Just x. Okay? Now, I give you the speed and also the time taken for this bar to move from here to here. So you actually can relate, okay, the velocity with the distance and time taken for it to move, okay, from this point to this point. Okay, so actually this one is we rewrite it and relate it with the velocity and time only. Okay, velocity is the u, right? How fast the sliding bar move. Okay, move for how long? Move for x. When you divide it with t, it will be the velocity. Is it? Do you understand the formula for velocity? The speed. Okay, someone runs 100 meters. Okay, and it takes 10 seconds. So what is his speed? You take the 100 meters divide with 10 seconds. Then you say that speed is 10. Am I right? Yeah. This is the same thing. You move this sliding bar for certain distance within certain time. Then you can get the speed. Okay, so this one is just rewrite only. Okay, faham? I hope faham lah eh. This one is the formula, so you get this one eh. So this is the first questions. Okay, B. Analyze the current flowing through the resistor R. Assume that the loop resistance, the Ri, is very very small than the physical resistance. Okay, so what you should do? Yes, you use V equals to IR. So your I will be V motional EMF. Okay, divide by the R, the physical resistance. So you have U square B naught T L V. No, this is not. Okay, and then divide with the. They give you the value of R? No. Okay. No. Ri is 0. How about the R? They didn't give you, right? So, but you cannot assume it to be 0. Okay? This one you remain, So this one will be your answer. Is it the same? Okay? The same thing, And the last one, illustrate the direction of the current flowing in your own drawing. So what you should do? You should draw something similar like this, am I right? Yeah. Then you should at least label the direction of the current. So what will be the direction of the current?
Opposite.
Okay, here, right? Okay, so now my magnetic field is pointing in the Z direction. So the current, it must produce something that opposes it. Am I right? Which is in this direction. Okay? In this direction. Okay, so can I change the color? Okay, so in this direction. Okay, so what will be the direction of your current? Right. So this one should be the direction of the magnetic field, which you're pointing in the negative Z direction. So your current should flow in this way. Okay. So your current should flow in this way. Alright. So this one should be positive here and negative here, right?
I think it's from negative and positive. Sorry.
Oh, okay. What? Yes. So this one is correct. Okay. So this one is positive. Okay, and this one is the negative. Okay, like a slide. My question is there any current here?
It's not moving.
Sorry. Is there any current here?
No.
Because this is an open circuit, right? So you only focus on the current here, okay? So this is what should appear in the section when you answer this question. Illustrate. So you have to draw something and show the direction. Maybe you label the I. Okay? Okay, so any questions?